India's rail network moves over 20 million people every day. To keep that grid functioning, operators require engines capable of dragging thousands of tons of steel, while strictly adhering to high-speed passenger timetables. Historically, locomotive design forced a choice. Engineers could either gear a motor to deliver immense low-end torque to pull massive weight, or they could gear it for high rotational velocity to reach top speeds. Combining these traits in a single machine involves a difficult physical compromise. In the late 1990s, the network already had a solution for the torque problem. This is the WAG-9, a heavy freight hauler designed specifically to drag immense cargo loads across the country at relatively low speeds. Instead of spending years developing an entirely new passenger engine from the ground up, Indian Railways engineers looked at the WAG-9's robust chassis and six-axle design. They realized the raw power was already there, it just needed to be redirected. By modifying a slow, heavy-duty freight platform, they created a rapid transit workhorse. The resulting WAP-7 is an exercise in mechanical adaptation. Adapting the platform for passenger use required a solution that could convert high torque into sustained rotational velocity. The solution was a precise mathematical shift in the gear ratio. They swapped the WAG-9's 5.133 freight ratio for a tighter 3.6, a 72-to-20 gear configuration. This sacrificed some lull-end grunt, but allowed the traction motors to spin fast enough to sustain passenger speeds of 140 kilometers per hour. That one ratio adjustment birthed the WAP-7. It proved that achieving high-speed passenger transit relies just as much on transmission mathematics as it does on raw horsepower. When deployed on major routes, the WAP-7 regularly hauls maximum length consists of 24 to 26 passenger coaches. That equates to dragging upwards of 1,500 tons of steel and human cargo at sustained speeds exceeding 110 kilometers per hour. The physical foundation supporting this is a 123-ton steel chassis riding on Coco Flexicoil bogies. 6 powered axles distribute weight and maintain traction. Those axles are driven by 6 three-phase induction motors. Together, they generate 6,120 continuous horsepower and a starting tractive effort of 322.4 kilonewtons. This torque provides a distinct operational advantage on steep mountain inclines, known locally as ghats. The WAP-7 can pull heavyweight AC trains up a 1 in 40 gradient single-handedly. This eliminates the need to halt the train and attach a rear banker engine for a push, saving 10 critical minutes off the schedule. The locomotive's reputation is built exactly on this hybrid capability, applying the relentless load capacity of a heavy freighter to maintain strict passenger timetables. The 25 kilovolt lines provide the raw power for propulsion, but the locomotive's onboard systems also manage the entire train's internal energy needs. To increase efficiency, the fleet integrated a system known as head-on generation, or HOG. HOG taps electricity directly from the locomotive's pantograph, converts it, and feeds it backward to power the air conditioning and lighting in the passenger coaches. This removes the need to haul diesel generator cars at either end of the train. A second major efficiency protocol activates when the locomotive navigates downhill descents: regenerative braking. During braking, traction motors reverse function to act as generators. The train's forward momentum spins the motors, creating electricity and returning up to 30% of kinetic energy to the overhead grid. This recovers roughly 700 units of electricity. Through these systems, the WAP-7 operates as a mobile power plant, actively supplying both its own passenger cars and the national grid. Since 2000, Chittaranjan Locomotive Works and other facilities have produced over 2,300 units, making the WAP-7 the most numerous passenger locomotive in India. Rather than retiring the platform as demand for speed increased, engineers continually updated its mechanical baseline. By implementing a revised 70-to-22 gear ratio, they created the WAP-7HS variant. This allowed the engine to reach 160 kilometers per hour, tailoring it specifically for premium services like the Rajdhani and Shatabdi expresses.
It was not designed merely to pull a train. It was designed to make powerful passenger operations routine. I want you to think about the sheer skill of that statement for a second. We aren't just talking about moving metal from point A to point B here. We're talking about mastering the logistics of one of the largest, most heavily trafficked railway networks on Earth every single day without even breaking a sweat. All right, let's jump right into the blueprint for today. We'll start by meeting the WT-7, then we'll look at the engineering powerhouse behind it, dig into its smart tech and efficiency, check out its performance on the tracks, and finally wrap up with its variance and legacy. Part 1. Meet the WAP-7, the workhorse journey. Let's start with a proper introduction to the most numerous passenger locomotives serving India today. Now, what's really fascinating about this contrast is how it brilliantly highlights the locomotive's widespread integration across the entire country. You've got the classic, standard white and red livery, which is instantly recognizable to millions of daily commuters, right alongside something truly special, a striking, highly customized yellow cheetah design. It just goes to show that the WAP-7 isn't just some standardized piece of equipment. It's become a canvas for regional railway sheds to display their local pride. It's a machine that's deeply woven into the very fabric of the nation's transit system. Tracing its timeline, you really see a machine that has continuously adapted. Developed by the Chittaranjan Locomotive Works back in 1999 as a passenger variant of a heavier freight locomotive, it made its first official run in May of 2000. But it didn't stop there. By 2019, a high-speed variant, the WAP-7HS, was introduced. Fast forward to 2025, and an aerodynamic version, the WAP-7AD, hit the rails. And to put its scale in perspective, as of August 2026, there's a massive active fleet of 2,316 units. This timeline proves we're looking at a living, breathing engineering platform that scales with the needs of the times. Moving on to Part 2, engineering a powerhouse, grounding the specs. Let's get into the physical hardware and explore exactly what makes this Titan capable of moving mountains. Just looking at this magnificent E-Road shed engine powering a train across a bridge, I really want you to appreciate the sheer mass of this machine. The locomotive alone weighs in at an immense 123 tons, and it sits on these fabricated Flexicoil Mark IV bogies. That heavy, incredibly durable foundation is absolutely crucial for maintaining stability when you're pulling massive loads at high speeds across all kinds of varied terrain. 6,120. That is a massive number, and it represents the continuous horsepower generated by this machine. To put that into perspective, this immense power is driven by 6 three-phase squirrel cage induction traction motors. It takes all that raw electrical energy and converts it into pure, unadulterated mechanical force, making it the most powerful passenger locomotive in the entire Indian Railways fleet. So the real question is, how does all that horsepower actually translate into real-world capability? Well, this locomotive boasts an incredible 322.4 kilonewtons of starting tractive effort. What does that actually mean for you as a passenger? It means this single machine can seamlessly haul massive 24-coach trains. We're talking upwards of 1,500 tons here at speeds up to 140 kilometers per hour. That right there is the very definition of making powerful passenger operations routine. Part 3. Smart tech and efficiency, brains behind the brawn. Because this locomotive isn't just about brute strength. Underneath that heavy steel shell, the internal engineering is packed with incredibly smart, highly efficient technology. Notice the striking red pantograph reaching up from the roof here. This isn't just some metal arm. It's the vital tether pulling 25 kilovolts of alternating current power straight from the overhead lines. But the real magic is what the locomotive actually does with that power once it pulls it down. And that brilliantly illustrates our next major technological leap, head-on generation, or HOG for short. Rather than just using electricity to turn the wheels, HOG technology takes that overhead power and routes it directly back into the passenger coaches. This completely eliminates the need for those noisy, polluting diesel generator cars that used to be attached to the ends of trains just to keep the lights and the AC running. The result? Massive savings in maintenance, a huge reduction in the carbon footprint, and significantly lower operating costs. It's a total game changer. Let's look at how this smart tech applies to some of the most challenging terrain out there, the steep GOT sections. Now, older methods required an extra engine, a banker engine, to attach to the back and push the train up the hill. The WAP-7 totally changed the game. By utilizing its immense power and advanced regenerative braking, it single-handedly navigates these inclines. It saves 10 minutes of operational time and recovers up to 700 units of electrical energy on the descent, completely eliminating the need for that extra push engine. This is efficiency operating on a massive scale. Part 4. performance on the tracks, real-world impact. So how do all these impressive specs, massive horsepower figures, and smart systems actually perform out on the immense, demanding Indian Railways network? Honestly, the track record is staggering. It provides phenomenal acceleration for mail and express trains, which reduces overall travel times. It routinely hauls 24 to 26 passenger coaches. Again, that's over 1,500 tons at speeds over 110 kilometers per hour. We already talked about the GATS, but it can literally climb a 1 in 40 incline while dragging 16 heavy AC coaches completely on its own. During trials, it even clocked a blistering 177 kilometers per hour. And perhaps most importantly for the future, its specific energy consumption is 15 to 25% less than conventional locomotives, meaning it heavily outperforms legacy diesel traction in both cost and environmental impact. When you see a classic WAP-7 just effortlessly pulling a seemingly endless passenger train, it all really clicks together. When you combine that 6,120 horsepower, the head-on generation systems, and the incredible tractive effort, you get a machine that handles the heavy, grueling, long-distance reality of daily transit with complete ease. This is exactly why it is the definitive workhorse. Part 5. Variance and Legacy. The future of the fleet. As the ultimate workhorse, the WAP-7 platform definitely hasn't remained static. It continues to evolve to meet the future demands of transit. Back in 2019, engineers pushed the platform even further by introducing the WAP-7HS. By modifying the gear ratio, they created a high-speed variant capable of maintaining 160 kilometers per hour while still hauling a full 24-coach load. This variant was specifically designed to push the limits of speed for premium services like the Shatabdi and Rajdhani Express trains, proving the platform's incredible versatility. And showing its modern progression, September 2025 saw the introduction of the WAP-7AD. This variant introduces a sleek aerodynamic redesign to the classic boxy shape. With an incredible maximum speed potential of 180 kilometers per hour, it was deployed specifically for modern high-profile routes like the Amrit Bharat Express. It proves that even a decades-old foundation can be optimized for cutting-edge modern speeds. This constant innovation, moving from a heavy freight derivative back in '99 to an aerodynamic high-speed marvel today, really solidifies its legacy. It stands unquestionably as the most successful passenger locomotive in the modern Indian Railways portfolio. It has literally redefined what's possible on the subcontinent's rail network. Which leaves us with a pretty fascinating thought to end on today. We've seen its brute strength, its smart energy-saving tech, and its aerodynamic evolutions. With continuous upgrades like high-speed gearing and these modern redesigns, just how far can the highly adaptable WAP-7 platform push the future limits of massive-scale rail travel? As engineering materials get lighter and power grids get smarter, could this titan keep breaking its own records for another 2 decades? Thank you so much for joining me for this explainer, and keep exploring the incredible engineering all around us. We are about to deconstruct something truly monumental. This explainer isn't just about a piece of machinery. We're looking at the mechanical spine of an entire nation's transport network, a machine of immense scale and unapologetic power. Just pure steel, electricity, and physics. Welcome to the anatomy of a titan. Every single day, millions of people rely on the uncompromising rhythm of the railway, but beneath the schedules, the tickets, and the bustling stations, there's a foundation of raw, heavy engineering that rarely gets the spotlight it deserves. Today, we're bringing that engineering out of the shadows. 6 powered axles, more than 6,000 horsepower, 25,000 volts of alternating current, and 6 traction motors working together. Every number tells the same story: controlled power. Just let those numbers sink in for a second. This isn't just about moving from point A to point B. It's about the absolute mastery of kinetic energy on a massive scale. It's about harnessing raw electrical violence to safely transport thousands of sleeping passengers through the dead of night. To wield that kind of power safely across thousands of kilometers of brutal and varied terrain, well, that requires a level of uncompromising engineering precision. And here it is, the WAP-7. You are staring at 123 tons of cold, hard industrial reality. This is the most powerful and by far the most numerous passenger locomotive in the entire Indian Railways fleet. Since it hit the tracks at the dawn of the millennium, it has become the absolute workhorse of the subcontinent. Think about it. It's the solitary machine responsible for dictating the schedule, the safety, and the comfort of millions of everyday commutes. But to truly grasp what makes this specific machine a titan, you have to look closely at its DNA. Now here's the wild part. The WAP-7 was never originally meant for passengers. Back in 1999, the engineers over at the Chittaranjan Locomotive Works looked at their existing WAG-9 platform. That was a heavy-hauling freight beast built to drag thousands of tons of coal at a slow, deliberate crawl. They desperately needed a new passenger engine, but they didn't start from scratch. Instead, they took on an incredibly audacious engineering challenge. How do you make a heavyweight boxer sprint like a track star? How exactly do you take a platform optimized for unyielding, slow brute force and refine it for high-speed, long-distance passenger travel? So, how do you execute that mechanical transition from a freight platform into a passenger titan? Well, the engineers relied on a brilliant yet fundamentally simple modification. They changed the gear ratio. In a freight locomotive like the WAG-9, the internal gearing is set for maximum torque, which is raw pulling power, but that comes at the expense of top speed. By modifying that gear ratio, the engineers allowed the WAP-7 to effortlessly trade some of that raw freight pulling force for significantly higher top speed. Think of it exactly like shifting a mountain bike from a low, grinding hill climbing gear into a high gear for a flat sprint. It's an elegant mechanical solution, perfectly optimized for lighter passenger loads, completely transforming the locomotive's entire purpose. At the heart of this newly geared sprinter lies one staggering number: 6,120. That is the continuous horsepower capacity of the WAP-7. We are not talking about a brief peak or a temporary burst of speed here. This is the continuous capacity it can effortlessly sustain for hours on end. That immense sustained power is exactly what allows this 123-ton machine to confidently haul massive 24-coach trains. And a 24-coach train is essentially a rolling village of thousands of people. It pulls all of that at a sustained 130 kilometers per hour, relentlessly fighting headwinds, gradients, and the sheer inertia of heavy steel. Let's dive into the core technical specifications, because this is where the physics absolutely come alive. We are talking about 25,000 volts of alternating current pulled directly from the overhead lines at 50 hertz. That massive electrical current is fed directly into 6 heavy-duty, 3-phase induction motors. These utilize what's known as a squirrel cage design. For those who might not know, that simply refers to an incredibly rugged, highly reliable internal rotor that uses simple conductive bars instead of fragile windings, making them virtually indestructible. All of this rests on what engineers call COCO-fabricated flexicoil Mark IV bogies. That means there are 2 massive wheel assemblies under the locomotive, each containing 3 powered axles. This specific design flawlessly distributes that massive 123-ton weight across 6 points of contact, ensuring maximum grip on the steel tracks, giving it a brutal starting tractive effort of 322.4 kilonewtons, all without crushing the rails beneath it. When you see this locomotive out in its natural habitat, it really puts the sheer scale of the operation into perspective. Sitting at the head of a massive 24-coach train, notice the overhead catenary network above. That single pantograph reaching up to kiss the high-voltage wire is the only umbilical cord powering this entire endeavor. The visual weight is just breathtaking. You have a single, solitary machine dictating the movement of hundreds of meters of steel and humanity trailing behind it. It represents the perfect marriage of civil engineering in the tracks, electrical engineering in the wires, and heavy mechanical engineering in the locomotive itself. But look, heavy engineering is never static, right? It's a constant, relentless pursuit of performance. Over the years, the WAP-7 has rigorously evolved. The original class hit a maximum design speed of 140 kilometers per hour using a 72-to-20 gear ratio. But as the transport demands of the country shifted and the need for speed increased, engineers refined the mechanics even further. The high-speed variant, the WAP-7HS, tweaked that ratio to 70-to-22, pushing the boundary to 160 kilometers per hour. And then we witness a massive conceptual leap to the latest aerodynamic iteration, pushing an astonishing 180 kilometers per hour with a vastly different 175-to-20 internal gearing. Each iteration proves the incredible versatility of the base mechanical design. Which brings us right to the cutting edge, introduced for 2025, the WAP-7AD. What's immediately noticeable is the sculpted aerodynamic profile. You see, when you push 180 kilometers per hour, the air itself becomes a formidable physical wall. Wind resistance increases exponentially with speed, meaning you need dramatically more power just to slice through the atmosphere. This specific streamlined variant was built to conquer that wall of air for premium high-speed express services, like the Amrit Bharat Express. It proves definitively that even a 25-year-old heavy haul platform can be sculpted and modernized into a high-speed bullet. But a modern Titan isn't defined solely by raw physical power and top speed. Moving a heavy train is really only half the battle. Stopping it safely and reliably powering the coaches behind it requires just as much sophisticated engineering brilliance. So let's shift our focus to the highly efficient electrical systems that elevate this locomotive from a simple brute force machine into a modern marvel of efficiency. And this is where it gets absolutely fascinating: regenerative braking. Think about the sheer physics of stopping 123 tons of locomotive plus thousands of tons of trailing passenger coaches from 130 kilometers per hour. Traditionally, you'd clamp down massive physical brake pads against the wheels, generating intense friction, and simply waste all that massive kinetic energy as heat bleeding off into the surrounding air. Not here. The locomotive essentially throws its internal electrical system into reverse. It turns its 6 powerful traction motors into electrical generators. As it slows down, it magnetically resists the rotation of the wheels, converting the train's massive forward momentum back into electricity and feeding it right back up into the overhead wire. It's an incredibly elegant way to recycle energy on a grand scale. Right alongside that regenerative capability, we have what's known as HOG, or head-on generation. Historically, a train of this size required entirely separate, massive diesel generator cars simply to supply the enormous volume of power required for the air conditioning, lighting, and fans for thousands of passengers. Head-on generation completely rewrites the rules. It pulls that massive 25 kilovolt power directly from the overhead lines through the locomotive's pantograph, converts it internally, and sends it straight back through heavy-duty cables to quietly power the entire train. By utilizing this system, the railways literally eliminate the need for those loud, polluting, fuel-hungry diesel generator cars that used to sit at the ends of the platform. Think about the massive real-world impact of that: the savings in diesel fuel, the reduction in mechanical maintenance, and the immense drop in carbon emissions are absolutely staggering. It replaces localized fossil fuels with centralized electric power. This is a prime example of how modern rail infrastructure isn't just about pushing the train forward, it's about powering the entire human ecosystem of the journey with uncompromising efficiency. You see the heavy machinery, you see the perfectly aligned steel tracks, and the complex overhead catenary lines above. 25,000 volts of raw power coursing down into a 123-ton Titan, turning invisible electricity into unstoppable physical motion. It regenerates power when it stops, and it silently feeds electricity back to thousands of passengers as they cross the continent. So how does this invisible web of electric power quietly run the backbone of a nation? It is a true testament to the uncompromising heavy engineering we've explored today. Until next time, keep questioning how the titans of our world actually work.